Hey guys, welcome to General Chemistry 2. We are going to start our journey in Chapter 10, talking about intermolecular forces and phase diagrams. Here is just a quick overview of what this chapter is going to look like. We'll have a series of videos to get us through this chapter, but just to give you a quick snapshot of the different sections that we are going to cover. So let me propose the following question. I'm gonna depict two chemicals on the screen. One of them is gonna be ethanol. One of them is gonna be dimethyl ether. Both of these molecules have the same number of atoms, 2 carbons, 6 hydrogens, 1 oxygen, which means both of them are gonna have the same mass. But what's going to be different is how all of those atoms are connected together. So here is our ethanol. So for ethanol, we see the 2 carbons, we see the 6 hydrogens, and we see the 1 oxygen. Some properties of this chemical ethanol. Ethanol is a liquid at room temperature, right? So ethanol is the main ingredient in your alcoholic beverages. Ethanol is known to be an intoxicating substance when ingested. Now let's take a look at dimethyl ether. So again, here we see the 2 carbons, the 6 hydrogens, and the 1 oxygen. So same atoms, same mass, different structure. Now let's look at some of the properties for dimethyl ether. First, dimethyl ether is a gas at room temperature, so it's in a completely different state. Dimethyl ether is used as an aerosol propellant, so in things like hairspray or bug spray or anything that needs to propel and spray sunscreen. It's used as an aerosol propellant. It's also used in compression ignitions and diesel engines. So exact same atoms, exact same mass, completely different properties. So one of the themes of our textbook that we've been talking about, if you took my course last semester, is that structure determines properties. So how all of these atoms are connected together is going to determine what properties we observe kind of in a macroscopic world. So what we're going to look at in this chapter is these interactions within the molecule. Why is this structure where we have a carbon, then an oxygen so vastly different than when we have a carbon, an oxygen, and a carbon, right? Why does that make these two molecules so different? So that's kind of a preview of what we're going to do in the intermolecular forces chapter. By the end of this chapter, we will be able to explain and understand why these two molecules are so different. Okay. We introduced this idea of ethanol as a liquid at room temperature, dimethyl ether as a gas at room temperature. So before we go any further, let's just take another dive into solids, liquids, and gases, our 3 states of matter, because this is going to continue to come up during this chapter. So here 3 states of matter: our solids, our liquids, and our gases. This is information that you've probably learned since you were in first grade. But let's just go ahead and review it here because it's going to play a big role in this chapter. So first we see our solids. So remember, solids are close, the atoms are packed very, very close together. Not a lot of room in between those atoms. They can vibrate or oscillate in place, but not a lot of freedom of movement. And they have this defined structure, right? Liquids are still close, very close together. They have a little bit of more freedom of movement, so they can kind of slip and slide past one another. But they still have indefinite shape, but they have a definite volume. They all kind of like to stay together. And then we've got our gases. Our gases are furthest apart. So we think of our gases of having little to no interaction with one another. They just kind of bounce freely. They take up the entire space of the container, so indefinite volume, indefinite shape. Okay? So that's just a quick overview of the three particles. Looking at what causes a state of matter. So how does something go from a solid to a liquid or a liquid to a solid? There's lots of different things that are at play here, okay? The first thing we learn about as young scientists is to go from a solid to a liquid or a liquid to solid is we can heat it up or we can cool it down. So if we think about water in this case, right? If we've got an ice cube, that's a solid. We apply heat. We put it in the room temperature. We put it on a stove. That solid is going to melt. It's going to change state and become a liquid. Conversely, if we've got liquid water and we want it to become an ice cube, we cool it down, right? We remove the heat and it becomes a solid. And we have the same thing over here with liquid and gas. So we've got liquid water. We put that liquid water on the stove, we heat it up, and it vaporizes, right? It becomes water vapor. We have water vapor and we cool it down. So it's a hot summer day, we cool down at night, that condenses back down into a liquid. Okay? So certainly temperature is at play here. Heat it up, cool it down, and we change state. But there's something else at play here, and that's what we want to focus on in this chapter. So when we look at solids, liquids, and gases, the other thing that's at play here is kinetic energy, that's the temperature piece, but also this molecular attraction piece. So we can talk about the attraction between the molecules inside this beaker. When we're talking about a liquid, we would say this has like an average kinetic energy. So kinetic energy is the energy of motion, right? Those particles can kind of slip and slide and move around. I want to focus on this molecular attraction piece. So for a liquid, we've got kind of an average molecular attraction. It's less than a solid, it's more than a gas, it's somewhere in the middle. But still, they're one another, right? Those particles stay close. When we talk about a solid, here we're talking about very, very high molecular attraction, right? Those atoms are in fixed positions, and the attraction between those particles is what holds them in that fixed position, that crystalline structure. So we've got very high molecular attraction here. And then if we go to the other end of the spectrum, the gas, no surprise here, there's very low molecular attraction. When we talked about the gas law chapter in the last semester, we talked about or ignored any attraction between those particles, right? So very, very low molecular attraction between those particles. So this chapter, we are going to look at this balance of kinetic energy and this molecular attraction. So here's kind of that summary statement. The state of a substance, so state being solid, liquid, gas, depends largely on this balance between kinetic energy and the attraction between the atoms or molecules. We have talked about this kinetic energy piece. We talked about it in the thermochemistry chapter last semester. This semester and in this chapter, we're going to focus on this attraction between molecules. That's going to be our focus point. So to summarize and to set us up for the next series of videos, we've got different types of attractions. What we have talked about up until this point is intramolecular attractions. So that's attractions within a molecule. We talked about things like ionic bonds, positives attracted to negative. We talked about things like covalent bonds where we're sharing electrons. So all of that happened within a molecule. What we're going to focus on in this chapter is intermolecular attractions. We're looking at interactions between two molecules. So I have a molecule on the left, I have a molecule on the right. How are those two molecules interacting with one another? Intermolecular forces, there's different types of intermolecular forces. And we've got 4 that we're going to talk about. Each of these will have its own kind of video presentation. But we're going to talk about London dispersion. We're going to talk about dipole-dipole. We're going to talk about hydrogen bonding. And we're going to talk about ion dipole. So each of those will have its own series of videos. This list is a hierarchy list. So as we move down the list, the intermolecular forces get stronger. So London dispersion will be our weakest, and ion dipole will be our strongest. One misconception that I want to knock out from the beginning is this. Those intramolecular forces, those ionic compounds, those covalent compounds, those are very, very, very strong. So these bonds are very short. We're talking about like 100 picometers distance between these 2 atoms. Shorter distance, stronger bond. The intermolecular forces that we're going to talk about are significantly weaker than those bonds. I'm going to talk about them like they're really, really strong, and they are at times. But they still, even the strongest intermolecular force pales in comparison to these bonds, right? So there's going to be a much larger distance here. It's going to be a weaker interaction than an actual bond. Very often we physically represent this with dotted lines. So our bonds are drawn with these solid lines. Intermolecular forces are typically drawn with some sort of dotted line to indicate that weaker interaction. That's your introduction to intermolecular forces. We'll continue the video series diving deeper into each one of those. I hope you found this helpful.